start. Welcome to our second plenary session. Very pleased to have Fredrik Johansson here, and he'll tell us about real numbers from a computational perspective.
So hi everyone, and thanks to Andy and the organizers for giving me the chance to speak at ANS for the first time. So the topic is how we can compute with real numbers and how to do this reliably, which it's a bit more difficult than over rationals or finite fields, for example, where everything is finite, can be represented explicitly. So how to compute reliably with real numbers? There are a few different ways you can try to do it, and none of them is going to be perfect. So we might have a bit of a car and a bit of a plane, and maybe something that is not perfect in either role. It will, of course, also depend on the application. I like to think that there are three kind of course paradigms or levels of real arithmetic. You can have just heuristic approximations, so floating point numbers. Or you can have a rigorous version where you track how large the errors are, so interval arithmetic. So that's level 2. And then you can have exact representations where you work with algebraic or symbolic expressions. And in a way, at each higher level, you get more certainty and you know more explicitly what's happening. But at the same time, you get a bit more restricted. There are fewer things you can do. It's more difficult to do things. And to varying degrees, computer algebra systems and mathematical software allows you to work at these different levels. So for example, in Sage, you might use the real field for level 1, or real interval field or real ball field for level 2. And there are a few options like QQ bar for algebraic numbers that are exact, or the symbolic ring if you want more general exact numbers. And myself, when I started working on mathematical software about 15 years ago, I created a Python library called MPMath, basically because I wanted to compute integrals and infinite series. This was entirely using this heuristic paradigm. And I guess then after a few years, I got fed up with things being wrong all the time, compute approximately, and you don't get the right result. You have to track down what's going wrong. And when you have a function that depends on several variables and you try to figure out what's going on, it gets really difficult. So a few years later, I started working on R, which is using interval arithmetic to get around this problem. And a few years ago, I also started working on a library called Calcium. I guess because I was fed up with things not being exact in R. So trying to do things, really do things exactly. And probably these levels works mod 3. So the next thing I will do is go back to doing heuristics again, because it's too limiting to do exact computations. But the point I'm going to try to convey in this talk is that there's not one kind of approach that is better than the others necessarily. In many applications, you actually want to combine them or use one or the other. This is also a bit orthogonal to the issue of formal proofs or formal verification, because you can do all these things in a proof assistant. You can have some heuristic computations that you then certify. And in terms of implementations, all the work I've done is C or Python code that can be full of bugs. I try to work pretty hard on testing things, and some of you use this software and do some really complicated things with it. And as long as no one finds any bugs, then least it's a good sign. So a fun application, and one of the first things I did with R, it's to compute the number of partitions of an integer. So you maybe seen this movie about Ramanujan. So this is a very nice scene from the movie where you actually see how you can compute the partition function from the ordinary Ramanujan series. So there you see terms that you add up, they get smaller, and you get something that is really close to an integer, and you round it to the right results. But if you look closely, you see that you have something that is 0, 0, 0, extremely small, and then things get larger again. So things are not really converging uniformly, and this is a pretty common situation that if you're not very careful, you can actually get the wrong result because you truncate your series at the wrong time, or you don't use enough precision. So something you can also see here is that the terms differ by many orders of magnitude. You have a few leading terms that are the size of the full numbers, and then you have a lot of small terms. So you have to be a bit careful with the precision. So I think the partition numbers are sequence 41 in OEIS. And you can also find this sequence, for example, numbers n were certain versions. So this is presumably because they were using the Rademacher series with the wrong error bounds. So there is an implementation in R that is very efficient and should be rigorous because it's using interval arithmetic together with a rigorous truncation bound. So another one example. So here I define A. It's my favorite mathematical constant, namely it's 0. So if you try to input this completely symbolically or exactly in computer algebra systems, and you put it into a matrix, for example, here A will be the 0 matrix, and B will be a non-zero matrix. And you ask computer algebra systems for the rank of these matrices. Then for the first one, Maple 2020, and the latest version of Sage will tell you that the 0 matrix has rank 1. Mathematica will tell you that the other non-zero matrix has rank 0. So this is something you can do with my calculus library. You can do this computations, and it will tell you that the rank of the 0 matrix is really 0, and the other matrix is really 1. So what's going on here? There's a few different things that can go wrong in computer algebra systems. One problem is kind of a default assumption that is built into the symbolic manipulation of computer algebra systems, which is that if symbolic expressions don't look exactly the same, then they are probably algebraically independent. So let's pretend that they are and compute that way. And this is correct almost all the time. It's correct until it's not correct. Right? So the proper way to do this is that you work with an ideal that represents all the algebraic relations. So this is easy for pure algebraic number fields or for transcendental fields. Does anyone know the status of this one?
It's not open.
Yeah, it's open. Algebraic independence of pi and e. So does this mean that you can't compute symbolically? Well, you can, you just have to be a bit careful. You have to check the computations as we go along. So it's basically that's what's going on in Maple and Sage on the previous slide. And the other kind of error that is very common is that to assume that if two things are very close numerically, then they are exactly the same. So this is what Mathematica believes. And I'm sure you have seen or know many examples like this of numbers that are very close, but not actually equal. That said, there are cases where we can use approximations to prove that things are really equal when we have a separation bound. So a famous example is the Moller-Bindnot bound for algebraic numbers. If we know or can bound their minimal polynomials, or even more simply with integers, if we know that something is an integer. And then, of course, there's the issue of actually implementing things correctly. But here, I don't think I need to give any examples. So if you actually want to compute exactly with real numbers or complex numbers and test if they are equal, you can use this kind of approach where you combine different techniques. So first, you can use interval arithmetic to try to prove that the numbers are not equal. And in some cases, you will have a separation bound, and then you can also prove that they are equal. If that fails, you try to express numbers in a common field. And then you can guess, so using heuristic computations, a relation among the generators of this field. And then prove it in a recursive way where you fall back on simpler fields. And then you check if after reducing things are zero, then you manage to prove the equality. And at this case, you might not know that you have found all the relations. If you can prove this, prove that all your generators are algebraically independent, for example, then you can also prove that things are not equal. But in general, you need to combine these two methods. So on the example I had previously with here with logarithms of two algebraic numbers, you could run LLL on these two logarithms and find that there is a linear dependence. Then recursive computations boil down to checking that the multiplicative identity over these algebraic numbers holds. And yeah, if at first you don't succeed, then you try again with higher precision, both for computing closures and for trying to find relations. And this might not converge, or this might not terminate. It does in some cases, like the algebraic numbers. And there is this result by Richardson that if Chauvel's conjecture is true, then in fact there is a version of this algorithm that terminates for elementary numbers built using logarithms and exponentials. But if there is a counterexample and you happen to input that, then this will run forever. So there are lots of issues how to really make this practical. So you can really work with exact numbers in a computer algebra system. How eagerly do you want to evaluate things algebraically or simplify things, compute perimeter basis and so on? How to choose the generators of fields you're working on. In general, you have a lot of flexibility. Very simple example is just if you want to use a multivariate or univariate representation of an algebraic number field, or if you're working with transcendental functions, what kind of base functions you want to use. Or if you have something like this, 5 + 1 raised to the 1000th power somewhere in your computations, you could keep that as a symbol, or you could try to expand it and use a simpler symbol, but then maybe you need bigger polynomials in your computations. There is also the issue of handling things where you would need really huge precision if you do things naively. There are tricks you can use, like exponential, some very small or very large number. Instead of just going ahead with numerical computation, you could use a kind of series expansion. So there's a lot of issues making this kind of exact arithmetic practical. And when you do things in a suboptimal way, it's not just that you lose a factor 2 in performance, you can lose a factor 1 million, or your computation never terminates. So it's a bit complicated. I will just show some benchmark results for simple computation. So I take a vector of exact real numbers. There's a few different sequences here. I compute the discrete Fourier transform of this exact vector, and then the inverse, and I subtract the original vector, and I prove that what I get in the end is the zero vector. If you try this kind of computation with different computer algebra systems, they will struggle. So for example, in Sage, you have a Q bar for algebraic numbers, the symbolic ring. And in many cases, they will simply not be able to do this. So what I'm doing in Calculum is that I'm trying to keep things more aggressively expanded. So I'm really trying to work in work algebraically in fields generated by these algebraic or transcendental numbers, instead of working with symbolic expressions and then in the end trying to simplify huge expressions. So that's a part of the reason why Calculum is a lot faster in most of these examples. So what I'm trying to express here is basically that you can use exact computations in some cases. It's maybe not what you want to do if you're computing with real numbers, complex numbers. You might want to use it as a reference. You have a numerical algorithm and you do something exact just to test it. Or in some cases, you have a numerical algorithm and it works most of the time, but maybe sometimes you have an input where it fails, and then you can fall back to doing something exact.
How do you define pi in the last two examples?
So here pi is the transcendental number pi. So
what does it know about pi?
So it knows that it's a transcendental number, but I don't know if it really knows it. Well, it's a philosophical question. But it's basically just doing arithmetic in a univariate formal function field. So it will be, I think in this case it's pretty easy because it will put everything in canonical form over the rationals over a rational function field, and it will automatically expand to zero when you do the calculations. But here, for example, where we have this sequence of roots of unity, of course, you cannot put this in a univariate cyclotomic field. Here, I put a star here actually. It's because, so in this case, so it's using, we'll use a multivariate representation with lots of roots of unity. And the star is because to make this work, I had to disable Grosvenor basis. So usually you want to compute a Grosvenor basis for the over the generators, over the ideals. So you keep things simplified, but in some cases it's actually better not to compute a Grosvenor basis.
So when you mean you compute the DFT, you mean that you sort of define these n variables, and then you have another n objects, you sort of write each one is an appropriate sum of these things, and then you create new variables with the inverse. Is that what you mean? Yeah,
well, so the way it works is that you write it just like you would write numerical code. You have constants like pi and functions like square root and log. And these automatically construct new fields containing the numbers you're using. And if you add two numbers, then it will compute the union of the fields. Also try to see if there are some relations.
What's the type of A after that first line?
Sorry?
What's the
Here?
type of A after that first line? Is it a float?
No. Well, it depends on the system here.
Type.
So yeah, I guess in Maple, it will be a symbolic expression. And
Oh,
also,
I see.
yeah, it will be a symbolic expression here. In Calculum, it will basically be an element of an embedded transcendental number field.
That's what you can.
Yeah. So I'm going to move on more to numerics. So if you want to compute with matrices and polynomials with numerical coefficients, I found that most of the time, just translating things into interval arithmetic works pretty well. And we have good performance algorithms for things like matrix multiplication and polynomial multiplication. Often you would have the issue that if you track errors rigorously, they will blow up when you do things like divide power series or invert matrices and so on. So typically for an object of size n, you lose the number of digits proportional to n. And then the question is, how do you work around that? You just increase the precision or choose a better algorithm. There's not a universal solution. You have to try different methods. And in some cases, it would simply not be the case that increasing the precision is enough. Like if you really have a discontinuity, like if you want to compute the rank of a matrix, just using numerics, it will not work. So either you have to change the problem or change the algorithm so you avoid discontinuity, or maybe you have two branches, you compute the rank 0 case and the rank 1 case, and then you combine them. But it's something you have to be aware of when you're doing any exact computations. Very useful method, very useful technique when doing interval arithmetic is not computing directly in interval arithmetic, but computing just an approximate solution, and then after that, you certify it. So a very classical example is solving a linear system, where it's kind of considered one of the great mysteries in numerical analysis, or one of the great happy circumstances that if you do Gaussian elimination and you track the worst case errors, even if the matrix is well conditioned, the error bounds blow up exponentially. But when you do it just in floating point arithmetic, you get almost perfect accuracy. So the best way to solve a large linear system is to do it approximately, and then certify the result. So this is in R. I did this with R in 53-bit precision. So A is just some random well-conditioned matrix. There's different algorithms for obtaining an approximate solution, doing interval Gaussian elimination, and then this posterior equation. And there are separate functions. So if you know what you're doing, you can just call the one you want. There is also a default function that's try to automatically select the best algorithm. So it will use interval Gaussian elimination if the precision is very large, because then it will be a bit faster. If you have a large matrix and low precision, then it will use the certification method. Another very important technique is combining different levels of precision for different numerical representations. I think this is, it's really an old idea, but it's becoming more and more popular right now. From my perspective, I think with hardware now, things are going in the wrong direction. For some time, we were getting larger, higher precision types. Now it's sort of going backwards. We're getting 32 bits and 16 bits, and even 8 bits. I think there's 8-bit floating points. Now, I think I even saw something about 4-bit floating points. It's not really anything. But I guess the idea is that for machine learning, since you're not computing the right thing, you don't need to do it with very high precision. Sort of, you're working with very large matrices, and it's more the structure of the matrix that's important than really the numerical values, and things are very self-correcting. Now, I think there's even kind of a trend that you don't even implement 64-bit floating point anymore in hardware, but you do 32 bits and then emulate 64 bits when you need it, because you don't need it with very high efficiency. But anyway, for our purposes, perhaps what's more important is starting with the machine precision computation and maybe extending it to double precision, couple of words precision, and then doing it in arbitrary precision. So this is something that has been used, for example, in polynomial root finding software like MPSolve. Uses this kind of multi-level, multi-precision arithmetic. And there's a really nice paper from just a couple of weeks ago about computing modular forms, where they take this well-known method where you set up a linear system for the coefficients, and you solve this to obtain numerical approximations of the degree of coefficients. Then you recover the algebraic expressions. And for this, the bottleneck is solving the linear system. So what they did is, instead of doing this directly in high precision arithmetic, they compute an approximate solution just using machine precision arithmetic, and they use this as a preconditioner, so as an approximate inverse. They use this to get initial values to do some iterative solving in higher precision. So I guess here they need the result with a few hundred digits of precision, something like that. But then you can do basically most of the work in low precision. So they got 2 orders of magnitude speed up. So for the rest of the talk, I will speak a bit more about analysis as opposed to algebra. So how to compute things really involving functions. And then the first question is, of course, how do you even represent a function? And if it's difficult to represent a real number, then it's probably even more difficult to represent a function, the real numbers, the complex numbers. So here again, there's kind of 2 paradigms, 2 approaches. You can work with general functions, and that means probably you can't represent them exactly, so you have to use some approximation or an enclosure. And there are different ways you can do it. You can use a function. The user just gives a function and that evaluates the function. So that's a black box. Or you can use some kind of polynomial approximant. Then if you want to handle singularities, you probably need something a bit more general. And then on the other hand, there's using special functions. So I don't think there is an agreed upon definition of what is a special function, but from a practical point of view, you could just call anything that you know exactly a special function. So typically, special functions can be described using differential equations or functional equations or algebraic equations. And this includes all things like elementary functions and L functions and modular forms that are also described by functional equations. And the advantage of using special functions is that potentially it can be much more efficient than using completely general purpose techniques, because we can if we have a function and we express our problem in terms of that function, we can then analyze all the properties of this function to evaluate numerically or handle special values. We can really do all the cases. But of course, it's also more limited, just like with exact arithmetic with numbers, because you will not be able to express every problem in terms of nicely behaved, well-known functions. So if you're computing with black box representations, what I mean by black box is that either you could evaluate the function in points and get approximations or enclosures of the values at particular points. And then, of course, the problem is that if you're just sampling, then in general, you don't know if you're going to miss some point where it suddenly does a huge jump. On the other hand, you could have actually an interval implementation, an interval black box, where you input an interval. Working. You can put an interval and gives you an interval as the output. And then if you want to compute things rigorously, you can subdivide intervals, which is a very powerful technique. But typically, if you want n digits of precision, then the complexity is going to be 2 to the n. So typically what you want to do is use error bounds or maybe the derivatives of the function, if you have them, and work with point values if you're working on this black box representation. So an alternative is to use approximate the function as a whole by a polynomial. The advantages are that but you get faster convergence, and you can reduce the effect that you tend to get overestimation when you work with intervals. And arithmetic with polynomials is pretty cheap, so you can do things like integrate, differentiate, or multiply, or compose pretty efficiently. So of course, this is completely standard in numerical analysis that represent things by polynomial approximations. So it's often used for a particular application. Just the first example that came to mind when I was preparing this slide was the method for computing L functions, where you have a nice Fourier series, truncated Fourier series, instead of having to evaluate more complicated transcendental functions. But you can also view this kind of representation as kind of data type for representing functions, just like floating point numbers or intervals. And then you can try to build kind of a system for doing analysis on top of this data type. So perhaps some of you have heard of the Chebfun project. So they're basically using Chebyshev approximations of functions. And their philosophy is that this is kind of the function analog of floating point arithmetic for numbers. So Chebfun is completely heuristic. It works pretty well for a lot of things, but there's no error bounds. But there are also vigorous implementations of this kind of approach. There are some projects using Chebyshev approximations together with error bounds and Coq interval. They are using Taylor models, so Taylor approximations together with error bounds, and they can do things like integration with rigorous error bound. So on the other hand, if you're using just black box evaluation, the situation where things are really nice is where you have holomorphic functions. Then just using the black box evaluation on enclosures, on complex intervals, you can often get close to optimal error bounds for point sampling. So a nice example is integration using Gauss-Legendre quadrature, where we have and write down this kind of bound where the error is bounded by the magnitude of the function on the ellipse surrounding your interval. And then you have something that decreases with this kind of radius around the bit. So you want to choose a large region around the interval if possible. So there's a trade-off that you want rho here to be as large as possible, because then you get faster convergence. But on the other hand, the function magnitude will get larger when you go further away. So you have to do a bit of balancing. But you can combine this with subdivision to make it adaptive, and this works really nicely. You can handle not just holomorphic functions, but piecewise holomorphic functions. So a fun example is this integral. I have computed it numerically with a few different systems. So a question for the audience: which of the results is correct?
Which one did you write?
Hmm? Right, it's none of them.
Where's the cop?
I didn't include it. Yeah, I should have.
The cop would be correct.
Huh?
The cop would be correct because
Yeah.
how they do exactly this.
Yeah, they did. I didn't put it here. I put so Chepfun actually gets it right. And yeah, I think Hawk interval, I think it's actually one of, I don't know if they had this particular example, but I know they can do this. You can also do it with R, and you can get a reverse result.
Many of the wrong answers agree. Is there a reason for that?
The what?
Many of the wrong answers agree.
Right. So the reason is that, well, for this integral, you have these three sort of peaks. And what happens here is that these systems, they will very accurately detect this peak, but completely miss this one. So basically what you get is a very good estimate for the integral, except for this peak, which is very narrow. Yeah.
When you say rigorous, you mean to successful places?
Yeah, I can compute it to a higher precision. So yeah, this is just rounded to 6. For this. Yeah. So this just kind of illustrates the computation, the way this implementation of adaptive Gauss-Legendre quadrature works in ARM. So that here you can see the subdivisions. It splits into smaller intervals. And this is a view in the complex plane. So the red dots here, it's the poles, the integrand. Here the poles are really close together, and you see that it's choosing ellipses that avoid the poles. So it's really holomorphic, and you get good error bounds. Now, a problem with interval arithmetic is that if you rewrite, so this took half a second to compute to 1,000 digits. If you rewrite the integrand a little bit, you can get a completely different performance. So instead of using the hyperbolic sec function, I use the hyperbolic cosine and divide, or I raise to a power and then divide. And suddenly things get a lot slower. And this is because when I divide, the error bounds blow up. So I end up needing much smaller intervals to get good bounds. So this is a problem with interval arithmetic that you have to be careful. Often you have to rewrite things manually. It would be nice to have good software with some kind of symbolic interface where software automatically rewrites things to make things more numerically stable, which could be possible at least for elementary problems. So here is a much more complicated integral that Harald Helfgott sent me a couple of years ago. He wanted to compute for some reason. So it's a really nasty function. It's well, you have thousands of branch paths, and you want to compute the square root, the absolute value. So it's not actually analytic, but we have to extend it, treat it as something that we extend to a piecewise holomorphic function. So I think the way we did this was that we manually implemented Taylor models, so locally expanding the Riemann zeta function into polynomials, and then integrating these polynomials along with error bounds. So this took a few hours to actually run the computation, to probably with a better, more specialized method, maybe better code for the Riemann zeta function for really getting optimal error bounds, you could do it more efficiently. Now, if you have functions that you want to integrate to infinity or integrands that blow up, you can't just work with the black box representation because you get infinity times infinity or infinity times 0. And either way, things will not converge. So you either have to truncate your integral manually or change variables or in some other ways, transform it to something that you handle with finite methods. And again, this is something that could be done in many cases automatically or semi-automatically using symbolic computation, which is a bit of an interesting problem. If you use Mathematica or Maple, they will use that kind of thing in many cases to do kind of symbolic analysis of your singularities, but in general, the numerical part, then it's not rigorous. So we don't know that the result is correct. I will also mention briefly that if you want to compute limits of sequences or series that don't converge quickly enough to get high precision, just using direct evaluation, there are very good convergence acceleration techniques. I will not go into detail here, but there's this very nice book by Henry Cohen and Wim Balabas that goes through a lot of different methods and how they work on different kinds of problems. And again, it's something where you would need to do some analysis by hand if you want the error bounds. And in some cases, this could be, I don't even know if there are error bounds for all these methods, probably not. In some cases there are, but not in general. So this is also a bit of an interesting research problem, I think, to get error bounds for convergence acceleration. So I will just mention that one of the applications of numerical integration is that we can use it to compute various special functions. Typically, this is not the most efficient way to compute a function. Different series expansions tend to be a better way, but it's a very flexible way. So if you want to cover the whole domain of a complicated function, it's often a very nice way to do it. So very briefly about special functions. A very nice class of special functions is the holonomic family, which are simply functions that can be defined using linear differential equations with linear coefficients. So famous example of most of the special functions you can think of that you would find in mathematical physics, for example, things like Bessel functions, or the error function, or the incomplete gamma function, things like that are holonomic. Hypergeometric functions are holonomic, and a useful example in the theory of L functions is that the inverse L transforms of gamma products is holonomic. And these functions have nice closure properties. So the sum of the product or the derivative or integral of a holonomic function is also holonomic. Some functions that are not holonomic are the quotients of two holonomic functions in general, or the gamma function or the Riemann zeta function. They don't satisfy a linear differential equation in this form. So what can you use these kind of special functions for? Basically, you can express a lot of things in terms of them and use the known properties to get exact results or to get numerical results more efficiently than with generic methods. So for holonomic functions, you can really compute things explicitly, like if you have two holonomic functions, you can express their sum their product explicitly. You can compute a differential equation for this. You can even decide if two functions are equal. can check that their initial values are equal. So this is used for a lot of symbolic computation applications for proving theorems. And you have very efficient numerical evaluation. So for many special functions, the most efficient way to evaluate them is to express them either directly or in terms of a series of volume functions, or in some other way, using properties or algorithms that we have for all numeric functions. So just to end the talk, I will go off a little bit of a tangent of the main topic, which is kind of reliable, how to compute with real numbers. So just want to talk a bit about work I've been doing that I did the last year. So someone complained to me that the gamma function in NARB was slow. So, and that person was Dan Schultz. So I decided to look at all the methods that there are to compute the gamma function and see if there was a more efficient way to do it. So I wrote a paper that investigates all the methods of the gamma function. I also found some new tricks to actually improve performance. So there are lots of different things you can do for the gamma function. There's the Stirling series, which is kind of the default algorithm, and in practice, it's also the most efficient most of the time. I found a nice little trick that you can take. So you have this sum over Bernoulli numbers. And you can split this sum in two parts. For the other parts, you use the Riemann zeta function instead of Bernoulli numbers. And then you rearrange, you use the series for the Riemann zeta function and you rearrange it. And then you get a double sum with a lot more terms than what you started with. But these terms are faster to evaluate because you can use hypergeometric series techniques. So in the end, this is actually faster. I've also been working on the incomplete gamma function because it's interesting for evaluating Dirichlet L functions. And I've implemented a lot of algorithms and a lot of cases, and I'm not completely done. It's handling, well, real parameters pretty well, or real argument and real parameter. But there are many more cases to handle it, and it's not clear how to do it optimally when you have large parameters. So just for these two functions, it's more than 20,000 lines of code in R. So I'm asking myself, I should try to generate this code somehow instead of doing all the cases by hand. But at the same time, it's pretty difficult to generate code for arbitrary precision arithmetic. There's not really an existing framework. So we'll see. But so yeah, for this fun application is that actually, if you want to evaluate Dirichlet L functions at special points, so at algebraic S, you can do it with subquadratic complexity in the number of digits. S is restricted in a certain way. And this is just using the fact that you can compute the incomplete gamma function. Another tangent, something I did after Andy invited me to speak here, and I had already decided what to present here. And if I had worked on this sooner, maybe I would have made a whole talk about this. But now it will just be one slide towards the end here, so it will be very quick. So for evaluating elementary functions numerically, there's a few different methods you can use. There's you can use argument reduction, and then you use series expansions. There are different techniques you can use to improve the complexity, so you get quasi-linear complexity with respect to the precision. And then another method is the AGM, which at least in theory is faster by a logarithmic factor. So there's this unpublished idea by Arnold Schoenhage. Well, there's a couple of published talk abstracts where he described this, but not really any details. So he had this idea that to reduce the arguments, you start with x and you want to make it smaller. You compute the linear approximation of two logarithms that approximates the number. And then you just compute this rational number and you evaluate the exponential of this small number. So he was doing this with the 2 or 3 prime numbers. And I think his conclusion was that it doesn't really scale to very high precision. But I recently realized that you can pretty easily extend this to use many primes, so 10 primes or 20 primes. And then you can get very high precision approximation of the argument. So here is an example, computing exponential of this number to 10,000 digits. And by implementation, it will compute this approximation very quickly. And then you just evaluate exponential of this very small number, about 10 to the minus 32. And this entire evaluation costs about 25 multiplications, so 10,000 digit multiplications, which is both empirical and theoretical. If you actually count the number of operations, you get roughly 25. This is about twice as fast as the AGM or methods using Taylor series. So what I'm doing here is that I'm using LLL to find these approximations, but I'm not using LLL directly at runtime. Instead, I have a pre-computed table, several relations, and then just using floating point arithmetic, I do reduction step by step by each relation. So I can compute this kind of approximation very quickly. Well, I guess the relation to the rest of the talk is that I'm actually using different kinds of arithmetic. I'm using an approximation, then I'm using it as part of actually a rigorous computation of the exponential function. So to conclude on topic, there are several representations you can use for real numbers, different paradigms. There is not necessarily an optimal solution for every application, but I think we can do a better job using rigorous methods instead of heuristic ones when we're trying to prove things. And it's typically very fun to look at a specific problem and try to optimize it and to find a really optimal algorithm. But it's also worth thinking about very general tools and how to integrate them and make them easy to use. Because right now, I think it's very often the case that mathematicians who are not necessarily interested in the problem, in the software, have to do a lot of low-level work, just getting things to run or having to figure out what's going on the software side, instead of focusing on the mathematics. So it's a bit of a problem that I try to work on. So that's everything. Thank you very much.
I have about 1,000 questions, but I'll try to just ask one. What with that, slides ago you mentioned the idea of code generation for this sort of thing.
Yeah.
What do you have in mind there? You mean like to sort of give some system a high-level description of the algorithm and then spit out the high-precision code? Or?
Yeah, so for example, for the incomplete gamma function, basically you have different infinite series that you're using in different cases. And you could generate from a symbolic representation of the infinite series, you could automatically compute error bounds and implement recurrence relations. What makes it complicated is that you're not just doing, well, you have to account for the structure of the series to do things efficiently. So there's actually a lot of low-level work, like you want to use the optimal precision for each term, and you want to multiply by small integers instead of full precision numbers and so on.
So R is written in C, right?
Yeah.
On the next slide, it can be required for compute with logarithms of high precision.
Yeah, so what I forgot to mention is that you want to pre-compute these logarithms. Yeah, you can do this. What I'm using is hypergeometric series, but I'm using hyperbolic arctangent. So you have these machine-like formulas. So in this paper, you can find I actually compute what I believe are the optimal, in a certain sense, formulas for simultaneous computation of the logarithms of the first and prime numbers. So in practice, pre-computing the logarithms that you need for a certain level of precision, it's about as expensive as one function evaluation or one or two function evaluations. So it's almost always worth it. Just do a little bit of extra work to pre-compute the logarithms, and then if you evaluate the function many times, you get a big speed up.
Shuna got idea pre-LLL.
Sorry?
Was this idea pre-LLL? Something like you think that?
No. It was like 10 years ago. A bit more.
So on the slide about polynomial functions,
Yeah.
you mentioned that you can't take ratios.
Yeah.
But in principle, there may be interesting examples that are with ratios.
Yeah.
Or 1/, even.
Yeah.
Are there any serious problems with working with those ratios that you don't have to worry about?
Well, so
zeros being very close together. Or,
yeah. Well, so algebraically, well, you can have a ring of polynomial functions, and then you just work in the fraction field. Also, there are extensions of the theory of polynomial functions to kind of higher level polynomial functions, where you have holonomic functions, so as coefficients. And there is an algorithmic theory for this, but it's not as well developed. So I don't know if you have closure properties or algorithms to all these things. And yeah, so one of the nice things of polynomial functions is that you have this, you can very explicitly compute the singularities. They're precisely at the roots of the leading polynomial. But when you have a ratio of two holonomic functions, then you can have arbitrarily ugly behavior. So things get more complicated.
So, yeah, I have 6 questions. The first one, the last questions are very specific. The first one is one which I am amazed that people haven't asked yet, but other people can ask it. So, are there plans to really put this together with Talk and with our other group verification systems? Because this is an issue.
Yeah.
We are striving to finally make computer systems as a tool.
Yeah.
And yet we could be making mistakes.
Yeah.
I mean, I was the second, so I used the library a lot, and you also have been using, well, say, Dave Flat's library, which is a very programmer around CR event, and yet correctly rounded mathematical library, CR that's right. But it's unclear where it says here and maybe it's completely correct.
Right.
Sometimes we different results from the car. And, well, maybe we could.
Well, I can also guarantee that ARB is not completely correct. I mean, it's a few 100,000 lines of C, so there are bugs.
Yeah. So if they're aiming at the truth, it might be a good idea to put it together with.
Yeah, I agree. And so I'm actually part of an ANR project led by Nicolas Crispard. That's the stated goal is to have a system actually where you can have different levels of just approximate numerical computations and then doing them with rigorous error bound, then being able to do the same thing with certified in COC. It's the stated goal of the project. I mean, I think in practice, the results will be that we will have some specific tools, and maybe in the end, perhaps a usable system that people can use, like a compute algebra system. But I think there are a lot of people that are interested in exactly the thing you're asking for.
Yeah, I mean, at least for the really basic functions.
Yes.
For a square event, it's about really basic functions. I mean, you cannot. Yeah, by the way, nobody here is going to actually be asking the input processor to compute or the ASD processor to compute sign of a number because it flies. So you have to use a library. But then it's a library telling us the truth, even for the sign, correct? Hopefully, but yeah, I do not know whether I had some more questions that were related to this.
Yeah. Just want to make one comment about that. I remember maybe about 10 or 15 years ago, there was a paper about a formally verified version of the square root routine in GMP. And I don't know if they actually verified the code that was actually in GMP, but the idea was that the code that was supposed to be in GMP had been checked in some system, and that was already a very difficult problem.
So there is a guy working on a formally verified subset of GMP.
Right.
So it's doing the MPN functions.
Oh, really?
I think it's actually generating MPN type code from, I don't know if it's talk or.
It's pretty hard because there's a lot of assembly code, isn't it?
Well, I think it's just doing the equivalent of the generic C base case algorithms. Maybe it's doing Parseval and some of them. In principle, you can have a formally verified GMP kernel that runs at the speed of generic C.
That's another question.
Yeah, so a few slides back, you mentioned when you're doing linear algebra, so it's actually also better to yeah, exactly. So there. So what do you mean by posterior certification?
So it can mean different things. Either you compute an approximate solution, and then, well, basically you compute the residual in interval arithmetic, and this gives you an error bound. Another version is, I think, is that basically you compute a preconditioner, so an approximate inverse of your matrix, and use that to solve the system.
Yeah, so basically you're getting a solution, and then you have a different equation.
Yes, you have
a known equal equal the matrix equals tiny, and
yes.
there is a small solution.
Yes, and in fact, at that point, you don't even need to do linear algebra. You can just bound the matrix. Well, depending on the quality of the bounds.
Actually, a question related to that. Are there any examples outside of linear algebra where you have the same sort of phenomena where floating point approximation, fixed floating point approximations are somehow magically accurate manipulation?
I can't think of anything off the top of my head. I'm sure I have seen some examples. So if I think a bit more, probably later, I can share that, but I can't think of anything right now.
I mean, I assume what's happening is somehow these errors are
Yeah, exactly.
out. And I can imagine that happening in other settings.
It happens. Yes.
Yeah,
Sure.
Yeah.
Back to your last slide.
So at the end,
Yes. I'd like to raise some limitable points about this. I think a lot of, well, not enough of us worry about these last points here, right? We tend to assume that when you do a computation in Magma or Stage or whatever, that you get the right answer, but it's not always true. And once you start worrying about this, you never stop. How do we get from where we are to where we should be?
well, people have to be interested.
Other questions?
Yes.
Okay, then let's thank Fredrik again.